So I want to spend this time to kind of continue comparing the independent betweens model ANOVA and the repeated within ANOVA. And again, just kind of looking at what theoretically the differences are and mathematically what those differences are. And then we're going to end up doing one more walkthrough of hand calculating the between subjects. So we're not going to do a hand calculation of the within subjects. So again, when we look at independent measures in ANOVA, we have that F is the MS between divided by MS within. We have our degrees of freedom is the number of groups minus 1. And the degrees of freedom within is the total number in the sample minus K. And again, we can use this to calculate this out. And again, if we're looking at the actual SPSS, our test of between subjects, we have our study type, which is actually our effect, and therefore we also then have our error. And taking this, and again, it's important to recognize that when we look at this, there's some important information here. So our sum of squares of study type is 2085. Divide that by 2, that's 10,042.5. Our error is 1,885. Again, divided by 27 is 69.815. So for instance, if all you had was degrees of freedom and mean squares, you could back calculate the sums of squares. You'd simply multiply the mean squares by the degrees of freedom, and that would give you your actual sums of squares. If you had your sums of squares and your degrees of freedom but not mean square, you would simply divide to get that value. Once we have that value, so again, our study type, our effect, mean squares is 1042.5, and our error is 89.815. We divide that, so the top number by the bottom number, and that gives us our F. And again, our F is 14.932, significance of 0.001 or less, and a partial eta squared of 0.525. Now, again, a reminder, this is the omnibus test. This says that there is a significant difference somewhere, which allows us to now do additional testing to find out where that difference is. And again, just a reminder that when partial eta square, kind of the rules of thumb is 0.01 is small, 0.01 to 0.09 is basically that small effect size, 0.09 to 0.25 is moderate, and anything over 0.25 is large. So with repeated measures, really it's the same equation, but we're replacing the bottom with just a measure of error. So again, we have our min squares between, sums of squares between divided by degrees of freedom between, but instead of actually within error, in other words, or within variance, we have error variance. We are no longer calculating the differences between the different people that are in the different groups. And again, we look at the degrees of freedom, and it's a little bit different. The between is the same, number of groups minus 1. However, the degrees of freedom error is the number of groups minus 1 multiplied by the number of people in any one group. It's always the same because it's the same people, minus 1. So again, this is how we'd report that. If we actually got this information in SPSS, it would look a little different. So this is the test of within subjects effects. And again, you'll notice that there's sphericity assumed, and then there's some additional information. Generally speaking, we're going to assume that sphericity has been assumed. It is one of the assumptions of the within subjects test, and it's one of the things that, again, ANOVA, when done in SPSS, is looking for. And you can take a look here as you see the other tests, the Greenhouse-Gauser, the Hunt-Felt, and the lower bound. What you see is the degrees of freedom gets less than 2. And the degrees of freedom for both error and effect are getting smaller with these various techniques. This basically, again, sphericity is a measure of, are we seeing variance beyond just the mean changing? It's similar to the Levene's test. And we can talk about that in more detail, but for this portion, we're going to assume sphericity is assumed. So again, we have study type. We have the same information that we would have gotten from a within's test. We've got the sums of squares, we got the degrees of freedom, and we got the mean squared. And that's our between groups effect info. We also have our error info. Again, we have the sums of squares, we have the degrees of freedom, and we have the actual value. That's our error info. And then to get F, again, we're simply going to take our between groups effect info divided by our error info. That's going to give us our F. We're then going to calculate what our significance is. And again, we're going to see what the effect size is. Notice the effect size does not change. So generally speaking, when we look at this, we're seeing the same effect sizes. But what we are seeing is a slight reduction in those numbers as we move forward. And if we look at significance, this is a fairly strong effect size. So we would find it no matter what, whether sphericity is there or not. But do notice that as we go to the lower bounds test, we actually go to a significance of 0.001. If this F was closer to 2 or 3, we would actually probably see it become insignificant and the effect sizes actually go down as we use these adjustments. This is just an example of a very strong test. So again, we get our statistical test. And again, because that partial of a square is above 0.25, this is a large effect. So let's just kind of talk about what's actually occurring in the numbers. This is actually the same data entered under the two different types of statistics. In other words, in this case, I'm violating an assumption. I actually have different people in different groups. However, I run the exact same data one time through as a independent measures where it's actually accurate. And the second time, I put the exact same data and I just pretend that it's the same people in each group. You're going to see what happens here. So the sums of squares is getting smaller on both sides. That's because, again, we're looking at those red lines. Those red lines are our repeated measures. That's where we have removed any measure of individual differences. So the numbers are going to be smaller, and also our degrees of freedom are going to be smaller. And then when we actually do the math, we end up with a stronger F, a larger F, 14.47. Again, this is the exact same data. It's just I'm inefficient. I'm basically breaking the rules of knowing what I'm doing when I'm running an ANOVA. In one case, the top one, the purpley blue, that's how it should actually be analyzed. I have three different groups with three different groups of people. But as I said, statistics are dumb. They don't know what we're doing. So I just told SPSS, actually treat this as if these are the exact same participants in each study, even though they're not. And I got a more powerful design. That's one of the reasons why it's very important that we are methodologically very sure what statistical technique we're using, because some techniques are more powerful, but they're specifically more powerful because of what they do and the type of data that they're meant to analyze. So let's go back to the between ANOVA, and all we're doing here is walking through another example of hand calculating the between ANOVA. So this is not the within, this is the between, where we have three different conditions with three different groups of people. They're independent of each other. And if you felt confident about this, there's really no reason for you to go through this. This is just another example using different data to kind of walk you through this process if you're struggling. So again, we're going to take a look at, in this case, I mentioned earlier the idea of comparing the t-test example we had of 6 hours of study versus 2 3-hour study sessions to a third category, no study, control. And again, I have the scores that the people scored on their test. Now this time I've summed it down to a much smaller score number, so we're not dealing with large numbers here. So again, under control, I have a 46546. Under 6 hours, I have 79775. And under 2 3-hour sessions, I have 10 10 9 8 8. So the first thing we're going to do again is we're going to calculate those means. Sorry. So I actually advanced it too quickly, but we're going to go through the same process. So what we're looking for again is we're actually calculating out that process to find out what's going on. So we're calculating the mean, we're subtracting each individual mean from that group's mean, and then we're squaring it, summing that up, and then dividing by the degrees of freedom. And that gives us these values. The first group, the control group, we have a 1. The 6-hour group, we have a 2. And the 2 3-hour groups, we have a 1. And this is our error. So this isn't our effect size. This is basically calculating whether or not we have what the error is, and we put that on the bottom of the equation. Now, as far as going through the second example, again, we've got our means of each group. In this case, control is 5. 6 hours is 7, and 2 3-hour sessions is 9. We calculate and add those up. 5 plus 7 plus 9, divide by 3. That becomes our grand mean. And then we'd subtract each mean from that grand mean, square it, and sum it together. And again, we'd run through and divide that by our degrees of freedom, which in this case is the number of groups, 3 of them minus 1, which is 2. So again, that's going to give us this value, and then we simply are going to plug those numbers in and actually do the calculation. So again, our MS between actually ends up being a 20. The bottom equation ends up being 1.34, and that gives us an F of 14.93. So again, our degrees of freedom are the number of groups minus 1, so 2. And within it's, again, the number of total of people multiplied in. So again, we've got 5 in each group, minus 1, minus 1, minus 1, or total number of participants, 15, minus the number of groups, 3. Either way, it comes up with 12. So again, we have an F2, 12, 14.93. We check that on our chart, see that we need a 3.88, and we now know we have statistical significance of at least 0.05. And now we're going to calculate that two keys HSD test. Again, we have them MS within. We have the total number of participants in any one group, and we're assuming it's going to be equal across these groups, and we just need to calculate that Q. And we do that from looking at the table. Again, we have 3 different groups, and we have 12 degrees of freedom error, so that Q becomes a 3.77. And we're just going to put that 3.77 in and calculate out those differences. So again, we have our 3 different groups. We actually can take a look and see what those differences are. The differences here is any difference over 1.96 is significant, and we find that they're actually all significant. In other words, the difference between control in 6 hour, control in 2 hours, and 6 hours and 3 hours, each one of those is a significant difference. So studying is better than not studying, but studying in blocks is better than just studying in mass. And again, there's the calculations that we'd run through using the numbers that we've already calculated.